KP Stats. This is lesson 6.3b. We're still on binomial distributions and variables, but now we're going to be talking about some means and standard deviations, how to measure them. Let's get started. So we're talking about mean and standard deviation of a binomial distribution. So we've already used bins to make sure it's binomial. We know n, number of trials, probability of successes. So we have the mean and standard deviation of x. They are n times p. This kind of gives you your expected value. And this is going to be the square root of n times p times 1 minus p. These are also in your formula sheet that you're given, that I gave you, but you're also given for the AP exam. Okay, they work only for binomial distributions. Make sure you remember that. So let's look at this example. Mrs. Desai gives a 10-item multiple choice quiz. You have to guess A through E for each question, and the answers are just random. She sounds like a monster, but whatever. I know there's some kids who just not like that. Patty from our last video, she's also in this class. She's just going to guess. So let's figure out what Mrs. Desai, what she can expect most students to get. Let's see. So mu of x is n times p, n is 10, p is 0.2. We got that because 1 out of 5 answer possibilities will be correct. That's 1/5, that's 0.2. So we just do 10 times 0.2, which is 2. So the answer, interpreting the value in context, on average, we would expect Patty to get 2 answers correct. So then find and interpret the standard deviation in this context of this binomial variable. So it's the square root of np times 1 minus p. So you just plug in your values, do the maths, and you get 1.2649. Interpret in context. This is not the interpretation. On average, the amount of correct guesses will vary from 2. This is your mu of x, by the way, by about 1.2649. This is the interpretation of the answer in context. Now, what's the probability that the number of Patty's guesses is more than 2 standard deviations above the mean? Sharing method. So what's the probability that her number of guesses is greater than 2 times the standard deviation? So this is how far away she has to go from the mean. That's where we're adding 2 to it. That equals probability x is greater than 4.5298, which is the same as saying what's the chances that she gets 5 or more right? She can't guess and get 4.5268 questions correct. That is not that's not possible. So we choose the nearest possible answer. This would put her above more than 2 standard deviations above the mean. This is the only way she can do it, by getting 5 or more. We do that by doing 1 minus the probability that she gets 4 or less correct, which is 1 minus 0.9672, which is 0.0328. It didn't ask for context, just the number. This is where it gets a little weird. Okay, I'm going to read this one. Suppose 10% of CDs from some company have defective copy protection schemes that can harm computers. Who uses CDs anymore? A music distributor inspects a simple random sample of 10 CDs from a shipment of 10,000. So we have X is the number of defective CDs. What's the probability that there are no defective CDs, that X is 0? It is not independent, okay? Because 10% are defective. So the actual probability is that there's no defective is, so there are 9,000 out of 10,000 that we know to be good, right? Because 10% of them are bad. This is the first of the 10 chosen. The next one, we want a success. So now there's 8,999 good, non-defective ones left out of 9,900, and so on. So you do this. This is 10 times, and you get what just happened? You get 0.3485. Now, if we use a binomial distribution, we're saying there's replacement, but there's not. We're not replacing them. When we sample them, we get 10 choose 0, that's 0.10 to the 0, that's 0.9 to the 10, that's 0.3487. These are very, very, very close. They're off by 2 10,000ths. So this is a good approximation as long as we don't sample more than 10% of the population. If our sample was 100, we'd still be fine. If it was 1,000, then we might start getting into trouble. So the independence rule, I want to use green. The independence rule, 10% sampling without replacement. So as long as, our sample is less than or equal to 0.1 of the population, so n is less than 0.1 times capital N, this is our population, it's reasonable to assume there are more than blah, 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 blah. Like we can do it. Or if the population's greater than or equal to 10 times the sample size, okay? So these are saying the same thing. If these are true, then we can use the binomial distribution as an approximation. Now, more approximating. Normal approximation for binomial distributions. So, as n, our sample, right, our number of trials gets larger and larger and larger, some things happen to the binomial distribution. So, it just becomes closer and closer and closer to normal, okay? These are histograms for different values of n and p down here, all right? So as a rule of thumb, we'll use the normal approximation when n is so large that n times p is greater than 10. So with Patty, it was 10 times 0.2, that equals 2. That is not greater than or equal to 10, so we could not use a normal approximation, right? Also, what also has to happen is n times 1 minus p must also be greater than or equal to 10. So really, this depends on n. Okay, expected number of successes and failures are both at least 10. It's kind of weird, but let's see it in practice. Go ahead and read this, and we're going to refer to it. Pause the video and read. Okay, so you read it. We're going to check bins to see if we can use binomial distribution as an approximation. We have two scenarios. They either have a debit card, success, or they don't have one, failure. So the binomial part is fine. The binary part is fine. They're binomial. So independent, the 10% rule. So P times N is P times N. No, it's N times 10 going to be greater than the total number of population. So basically it's saying, is it reasonable to assume that there are more than 10 times 506 teens age 14 through 18, so in this case 5,060, in the U.S.? Yes, it's pretty reasonable to assume that. So they are independent. And then there's 506 trials. It tells us that. That's our lowercase n. And then P, the chance of success, is 0.10. I don't know how they would determine that we know exactly 10% of all teenagers have a debit card. So we're good. And then check the conditions for using normal approximation. So now we've checked that n, lowercase n times p, so our sample number times our probability of success, is that greater than 10? Well, 506 times 0.1, yes, that's 50.6. It's bigger than 10. Same thing, our number of our in our sample times the probability of failure, which is the complement here, is that greater than 10? And yes, you do the maths, you get 455.4 is greater than 10. So what does that mean? It means we can use the normal CDF instead of binomial CDF. So now they're saying, what's the probability that 40 or fewer of the teens in the sample of 506 have debit cards? So that's the probability that X, number that have a teen has a debit card, number of teens is less than or equal to 40. There's a lot going on here. So we talked about this. What's the mu? What's the mean of this distribution? Well, that's going to be n times p. That's 50.6. We got that up here. The standard deviation is n times p times 1 minus p. So you do the maths, and you get 6.748. We use a positive value. So I have a normal distribution. I'm using a normal approximation for this binomial distribution, 50.6 and 6.748. I can standardize this statistic, and so I get 40 minus 50.6. This is our probability we're looking at, right? This is our boundary, divided by 6.48. And my z-score is negative 1.5708, or negative 1.57. So here's my normal curve. This is the mean, and I'm looking for the probability that in this sample, there are 40 or fewer teens with debit cards. So my calculator, because we're using normal CDF, negative infinity, is the lower bound, upper bound is lower bound. Upper bound is 40. The mean is 50.6, that's right there. Standard deviation, 6.748, we got that from here. Or if you want to use your z-score, your standardized statistic, your lower bound is still negative infinity, but this time our upper bound is negative 1.5708, or just 1.57. Your mean is 0. Remember, when we standardize it, our mean is now 0, and our standard deviation is 1. Doesn't matter which one you use, you'll get the same answer, 0.0581. Also, I plugged it in using the binomial CDF, and that got me 0.0637. These are very close. They're off by a little less than a hundredth. And so just remember this part, that the criteria, bin still applies even if there's no replacement, but your sample and your population are substantially large enough, you can assume independence right here because of the 10% rule. All right? So, hope this is helpful. If you have any questions, you know how to get a hold of me.